Okay, everyone. Apologies for the now familiar technical delays, but we are finally ready. So it's a great pleasure today to have our local hero, Dominik Ehrenfels, speaking. Dominik did degrees in both physics and philosophy at LMU Munich before coming to Oxford in 2018, I think, as a BPhil student and then DPhil student. Working with Adam, and you're coming to the end of that, so it's come time for you to endure the trial by fire that is the Thursday seminar. So, Dominik, over to you.
Great, thanks very much. So today's talk is going to be about a chapter of my thesis about different ways of reformulating theories. My thesis supervised by Adam, so I couldn't have ever asked for a kind of more generous, wonderful supervisor. I'm really tremendously grateful to him for all the support over the years. This particular chapter, James has also given me very, very helpful comments on it, as have many other people. So, let's see, how can I see, I think I have to click on it to make it move. But I don't know how to go back then. Right. We'll figure that out later. The old tale is old as time, so symmetries are often an indicator of surplus structure, and recently we now have two strategies for getting rid of it. So there's the reduction strategy, and then in recent years Neil Dewar has coined this term sophistication for a separate strategy for dealing with surplus structure. And I suppose with reduction, the idea would be to eliminate a symmetry to core. So this is usually achieved by formulating a new theory in terms of symmetry invariant quantities of the old theory. So one standard example that everyone knows is, in electrodynamics we have a vector potential, and that has a gauge symmetry, and then the Faraday tensor is what's one thing that's invariant under that symmetry, and we can rewrite the theory in terms of that, and that would be a reduction of the theory. We end up with a new theory that doesn't have that gauge symmetry anymore. Right. With sophistication, which is what Neil has advocated, we do something else. We retain the symmetry, but we make sure when we reformulate that we only have the symmetry relate models that are isomorphic. And then it becomes arguable, I suppose, that there's no more surplus structure here because any two symmetry related models agree on all structure, they're isomorphic, so it doesn't look as though any of the structure is surplus anymore. And the analog of reducing electrodynamics with the vector potential would be to move to something called the fiber bundle formulation, where we still have those transformations, but they now relate isomorphic models. Right. So which one should we go for? Which strategy is better? I think reduction was along the sort of the paradigm of reformulation. It was sort of the only game in town. But my impression is, at least, that recently sophistication has gained a lot of traction. We even to the extent that I think it sort of has dethroned reduction, and it's sort of been accompanied by this breakthrough in metaphysics as well, where people have thought of it as sort of in conjunction with these sophisticated substantivalist doctrines, or this anti-hexaetism that's supposed to then help with sort of worries about underdetermination further down the road. But so what I want to do in this talk is to sort of say, well, let's not write off reduction too quickly. The issue, well, so proponents of sophistication, for instance, Neil in his paper, they have some various criticisms of reduction, and one of these is that reductions are thought to be sort of very difficult to come by. We don't always know how to construct them, and well, I think that's true to a point, but I think there's sort of two culprits for that. One is that there's this idea that the way to reduce is to explicitly reformulate in terms of symmetry invariant quantities. And the second is to demand that reduction always has to lead to a theory that is fully empirically equivalent to the theory we started with, the theory that we're trying to reduce. And I will argue that, if we can have those things, that's nice, but we don't always have to have those things in order to find a successful reduction. They're worth having, but they're not essential. And if we drop them, this will lead to a sort of more fruitful, more inclusive notion of reduction. So I'm going to proceed is I'm going to look at a success case of sophistication, which is the scale symmetry of Newtonian gravitation theory. And then I'm going to introduce, so we're going to see that this is a success for sophistication. And then the question, of course, becomes, well, can we also reduce the theory with respect to that symmetry? And there, I'm going to think a little bit harder in section 2 about what actually is involved in reduction. And I'm going to sort of identify three sort of principles, three conditions that people have sort of thought to be constitutive, perhaps, of the idea of reduction. And I'm going to say that if we hold on to these principles, then it's going to look pretty bleak. It probably doesn't look like we can find a nice reduction of Newtonian gravitation theory with respect to that scale symmetry. But I want to then sort of take a step back and look at lessons from the history of relationalism for how to best reformulate theories. And I think that these lessons are going to teach us a lot about how to sort of demotivate these three principles and maybe do without them. And I will show then that once we think about reduction in a sort of more inclusive way, then we can find a good reduction of NGT with respect to the scale symmetry. And then I'm going to compare the theory we are going to find with that sophistication of Newtonian gravitation theory. Okay, so let's start out with the sophistication, because that's sort of our rival today. I'm going to see if we can compete with them. So the scale symmetry is a symmetry of Newtonian gravitation theory, and the presentation of Newtonian gravitation theory that I'm going to use is just taken from one of Casper's papers, where we have a finite set of particles, we have a three-dimensional Euclidean affine space, and a one-dimensional Euclidean affine space that is for time. And then we have the particle trajectories in there, and we have an assignment of masses to the particles, and those take values in the positive reals. So we assign to each particle some positive mass in the reals, and then we have that all governed by the usual equations of motion. Now, what is the symmetry of this theory that I'm going to focus on? Well, I call it the scale symmetry. The scale symmetry is a simultaneous rescaling of the interparticle distances by a factor lambda, the durations between events by a factor tau, and the particle masses by a factor mu, subject to a certain constraint, which is lambda cubed equal to mu tau squared. So if you do it subject to this constraint, then you preserve solutionhood and you get another solution. And people have looked at this symmetry, and Neil has offered a sophistication. Neil was actually first, but the paper was not published for a long time. And then Casper has published a slightly improved version, a slightly different version. We'll look at Casper's theory. So the problem, of course, as the sophisticator sees it, is not so much that there is this symmetry, but that it relates models that aren't isomorphic, right? So if you rescale according to what it says, then you end up with a model that just isn't isomorphic to the one you started with. How can we fix that? Well, I think the basic insight that Neil and Casper offered here is that the value spaces that we're working with are too highly structured. So we might have some reason to think, for instance, that representing, for instance, mass value space by the positive reals just imputes too much structure to it. It would be more adequate to think of the kind of structure we think mass quantities to have to involve, well, what is called an additive extensive structure. So what we should think the structure of mass value space is that we have some continuous size space set. This is sort of the mass quantities that an object can exhibit, and then these are totally ordered. We have a total order on that, and we have a concatenation function on that, which tells me sort of, if I take this mass and this mass together, then I get this third mass, right? But this structure is of it's not as highly structured as the positive reals. It's a non-rigid structure because it has this automorphism of uniform rescaling. That's one automorphism of the structure, and that might strike us as a more appropriate representation of mass value space. So we can do this, and we can sort of run through the same reasoning for distance value space and duration value space, right? So maybe these also strike us as the kind of thing that should be more appropriately represented by these kinds of structures. And we can do this, and this is essentially how Casper proceeds, right? But then we face a sort of problem, which is that we're now working with structures that are sort of individually invariant under rescalings. But of course, as we know, in isolation, a mass scaling is not a symmetry of Newtonian gravitation theory, nor is it distance scaling, right? So if I take some solution of Newtonian gravitation theory and then I make everything twice as heavy, I'm going to notice some differences in behavior. It's not going to be It's not going to be an indistinguishable solution. So, or it might not be. Yeah. Solution at all if I keep the trajectories fixed. So the solution that Casper comes up with is to rethink the status of the gravitational constant. He sort of thinks of it as not a constant, but as a cross value space function that sort of use these value spaces together in the appropriate way, so that we get to exactly the appropriate amount of structure that we need, and then we get this theory, SNGT I'm calling it, where we incorporate all of this, and we end up with, we replace the Euclidean affine space with something I call a Weylian affine space. Weil, like this idea of scale invariance, so I named it after him. I don't know if there's an actual name for this structure in the literature. And then we think of G as this function now instead of a constant, which takes me to accelerations in a sort of appropriate way. And the crucial thing about this new theory is, of course, that we still have these rescalings as a symmetry, but now they relate isomorphic models. So this sort of counts as a sophistication of the theory. We can rescale, but we end up with an isomorphic model. Okay, so this is sort of the bar that reduction now needs to meet, right? So we have a sophistication with respect to that scale symmetry. We don't have a reduction. So if I'm going to argue that reduction is worthwhile, reduction is sort of a good strategy for dealing with surplus structure, then I sort of need to make some progress here and sort of give a reduction of the theory with respect to the scale symmetry. And well, to do this, I think the starting point should be to think a bit more carefully about what we mean by reduction, what's supposed to be involved in reduction. And I think going through the literature on this, I've sort of identified 3 criteria or 3 conditions that a successful reduction needs to meet according to a lot of people. And so I'm going to talk about these in a moment, but I will argue that each of these should be relaxed, because if we hold on to these 3, then it's unlikely that we're going to find a good reduction of NGT with respect to the scale symmetry. So the first condition is that we should think of so let me just read it out maybe. So a theory can only be said to be a reduction of a theory T with respect to some symmetry. That should be a theory T prime. Can only be said to be a reduction of a theory T with respect to some symmetry of T. So we're only in the ballpark of reduction if we're looking at one theory that has a symmetry and then we're eliminating that. So if T is a theory with a symmetry H, then reduction of theory R of T is a reduction of T with respect to H only if the reduction possesses no analog of the symmetry H.
Would it be better to say that the only prior analog is the identity, or something like that?
Sure. Yeah. Maybe I should say that. Yeah. So throughout, I've not been so terribly careful with those things. Maybe that may, but I hope that sort of the idea is clear at least. That the analog would be the identity. So why relax this condition? Well, I think that we have seen a motivation for this already, so to speak, because when we thought about how to represent mass value space, well, we sort of said, well, we might have motivations for thinking that we would want mass value space not to be represented by some rigid structure like the positive reals, but by some structure that admits of scalings. And even though scalings are not a symmetry of Newtonian gravitation theory. So the idea here would be something like, look, I can sort of worry that I've misrepresented a particular value space in my theory. I can try to reduce with respect to that without worrying whether the symmetries I want to see in my adequate representation of that value space are actually symmetries that I find in the theory. So, if we think that mass value space should be is invariant under uniform scalings, then, well, if I'm going to be in the spirit of reduction, I can find the invariants of those scalings, which are the mass ratios. So those are preserved, right? So if I'm in this reductivist spirit, then I might want to reformulate Newtonian gravitation theory using just mass ratios. And this has been done by Niels Martens. I mean, his motivations are different. He just wants to find comparativist theory, but I think you can at least tell a story of this kind to get to the idea that we should want, maybe a mass comparative version of Newtonian gravitation theory. And the way he does it is that he introduces, so if we just have, let just mu I be the ratio of the mass of the ith particle to the total mass of the sum of all masses, then we can find a new theory with the following equations of motion. We have some new constant gamma, and we replace mi with mu I. Oh, sorry, this should be an I there. And so the tricky question here is then: is this new theory that Niels comes up with, is this empirically equivalent to Newtonian gravitation theory? So Niels gives us a very extended argument that it is, which relies on some controversial assumptions, but I would argue that it's actually fairly straightforwardly empirically equivalent to Newtonian gravitation free, because for every model of NGT, we can choose some appropriate value of gamma such that the corresponding MC model then replicates all the right trajectories. So the trick to making them empirically equivalent is just to let the choice of gamma sort of depend on the model the model of NGT that you're trying to replicate, to capture. Okay, so the second condition that I think a lot of people impose on reduction is what I would call the explicit invariance condition. So what I mean by that is that a reduction of a theory T with respect to some symmetry H must be formulated explicitly in terms of symmetry invariant quantities that are definable in the old theory T. And the basic idea is to find new dynamic equations which feature only the symmetry invariant quantities that we want to be committed to, say, if we're looking for this reduction. So this condition is something that's sort of fairly explicit when Neil in his paper describes reduction and sophistication. So he explicitly thinks about reduction in this way of sort of finding new equations that only involve the symmetry invariant quantities. Why should we not have this condition? Well, I think we have. This is something we can discuss in the Q&A, but I think we have powerful tools for indirectly characterizing structure. And this will become later on. I think we just can do much more if we don't insist on this. And this is something I'll talk more about later. But one example here would be sort of Ehrman's original definition of Maxwell spacetime, for instance, uses this equivalence class of affine connections. And I think that's fine. Essentially, I don't worry too much about trying to find what the invariant of common to these is. If for those who are familiar with this, one can define a sort of geometrical object with this curly arrow of Weatherall's, but we don't really know so well how to use it. I don't think we can write down equations. We know?
We can write down equations. I did that.
Oh, you did that. Fantastic. Well,
that was my undergrad thesis.
Oh, okay. Fantastic. Well, I do apologize, but I can't do it. Some more gifted people can. So that's fine. But for a long time anyway, the status quo was that we didn't know how to do it. And I think that Ehrman's formulation is sort of just fine for most intents and purposes. Obviously, it's great to have the intrinsic formulation, so to speak, but it's not a must-have, I would say. It's sometimes alleged, so Casper has a paper on this, that intrinsic formulation has some epistemological advantages, but that strikes me as false in general. I think we have a perfectly clear grasp of the structure Ehrman was defining, and we had that hopefully even before we fully knew how to define it intrinsically. So I think the explicit invariance condition goes too far, and Neil is sort of wrong for insisting on it. The final of the three conditions is what I call the empirical equivalence condition. So pretty straightforward. Any reduction of a theory T must be empirically equivalent to T. And this empirical equivalence is to be established via a process called model recovery. What do I mean by that? Well, the canonical example of this would be Troutman recovery. So the way that Newton-Cartan theory recovers Newtonian gravitation theory, and the idea would be that T prime recovers the models of T just in case T prime contains one model up to isomorphism for every equivalence class of symmetry related models of the original theory, and for each equivalence class the unique model of the new theory is a substructure that is common to the models in And well, you know, that substructure is of course supposed to be sort of rich enough still to support the right dynamics. So we want that model obviously to be empirically equivalent to the original models. So why should we relax the empirical equivalence condition? Well, we'll see later on that it sort of has sort of precedence when we think about the history of relationalism. But I could think of sort of two motivations for the empirical equivalence condition, and neither of these strike me as terribly compelling. So the first would be that we shouldn't sacrifice empirical adequacy for the sake of structural parsimony. And the second would be that if we think about what we want reduction to be, what is reduction in the first place, we might think of reduction as the sort of thing that's sort of supposed to separate the wheat from the chaff. We want to eliminate surplus structure, but retain all the sort of physical structure, the dynamically efficacious structure. And I take it that that's the idea that's sort of incorporated in this model recovery condition, right? I don't find either one of these terribly compelling. So the first was don't sacrifice empirical adequacy for structural parsimony. Fair enough, of course not. But that's still consistent with finding an empirically more predictive theory as that we can use our reduction, or we can find a reduction that is sort of sufficiently empirically equivalent, but not quite, sort of approximately empirically equivalent. So obviously we're going to be most interested in reducing empirically successful theories, but that does not mean that we have to recover all of the empirical predictions precisely. So, you know, that motivation doesn't strike me as terribly good. And then the second motivation was that sort of it's constitutive in some way of reduction, that it's supposed to separate the wheat from the chaff. It's supposed to give us sort of the theory laid bare, stripped of surplus structure. That strikes me as sort of artificially restrictive. I find that sort of very limiting. If the aim of reduction is to uncover what structure we should think of as physical or sort of actually out there in the world, then any and all suspicious structure in the theory, I think, should be a target for elimination. And I think the just focusing on the structure that's sort of dynamically inert is artificially restrictive there. So I got some examples here of dynamically sort of essential but dubious structure. In Lorenz's ether theory, we find a standard of rest. So Clara Bradley has discussed this in the paper. And this is non-eliminable in any sort of, or at least it doesn't fit the bill for surplus structure. It sort of plays a clear role in the theory. I think that when it comes to sort of extending Bohmian mechanics to relativistic physics, we need to sort of come up with some preferred foliation. Again, not great. It doesn't strike us as, I mean, maybe we have to go for it, but it doesn't strike us as the kind of thing we would like to have. And then in Newtonian gravitation theory, sort of relationalists, such as Julian Barber and so forth, are very skeptical of the inertial structure and the temporal metric. Yeah. So these are all examples of structure that plays a dynamical role, but that we might still regard with suspicion for various reasons and that we might want to eliminate. And, so I think the idea would be something like if the idea behind the empirical equivalence condition is that we shouldn't throw out the baby with the bathwater, we shouldn't throw out dynamically essential structure together with surplus structure, then I think these examples sort of show, like if the baby is sort of ugly enough, we might want to throw it out anyway, right? So I see no real good reason for limiting the aims of reduction to eliminating surplus structure. Okay, so we've looked at these three conditions that I think are sort of very much part of the canonical way of thinking about reduction. Maybe some of you will say, "Well, I never thought about reduction this way," which good for you. Then you were right all along, so to speak. But I mean, looking at the literature, I certainly think that a lot of people think about reduction this way. I I mean, a lot of this is at least implicit in the way Neil writes about it. Also, if you think back to Niels Martin's theory of Machian comparativism, what was striking there was that he gives a mass comparativist treatment, but he does not give a sort of relationalist treatment or anything like that. And the reason he doesn't is that he says this explicitly, he's looking for a theory that is empirically equivalent to Newtonian gravitation theory. He's not concerned with trying to break out of that. So I think in his paper, and in many ways it would be more satisfying as opposed to give a sort of unified comparativist and relationalist treatment. But he refrains from doing that precisely because he wants to hold on to the empirical equivalence condition. So I do think that these are sort of very much baked into the canonical way of thinking about reduction. Okay, so let's go back then to the scale symmetry. We have seen that we can sophisticate it with we can sophisticate Newtonian gravitation theory with respect to this scale symmetry, but the question that we were asking is can we also find a reduction? And having sort of outlined what I call the narrow view of reduction, it looks extremely tricky. It's not clear that we can do it. What do we have to work with? Not very much. What's preserved under this transformation? Well, we have distance ratios, spatial and temporal. We have mass ratios. Taking those two together, that's hardly going to be enough. Doesn't look very promising. And then what we can add to the mix is the ratio of spatial distances cubed to masses and temporal distances squared. So this is sort of that's another invariant of the symmetry as captured by this side constraint. And so we can work with those three things. Working with the third of these strikes me as extremely ad hoc. I wouldn't know where to begin with that. I don't know how to write down equations where I incorporate these ratios. But I think there's a more compelling reason still for not even trying to go there, which is that just if you try to think a little bit about the what metaphysical interpretation you would want to give of a theory that looks like this. Well, so David Baker has sort of tentatively explored this idea of having a comparativism with mixed quantities. So comparativism where your basic quantities don't just involve things like mass ratios or distance ratios, but also sort of distance to mass ratios. But there are many problems with this. And one problem there is that these will have to take some numerical value, and the numerical value that you assign to, for instance, a distance to mass ratio will obviously depend on a choice of units. So it looks as though if you're going down that route, you're actually taking a step in the wrong direction in a way, because you're sort of reintroducing a preferred unit, which is what, when we looked at the sophistication of recurrent gravitational theory, was of one thing that we tried to avoid. We didn't want to go there. We didn't want to single out the kilogram as sort of a preferred unit, right? And it looks as though if you're going to go down this route of opting for mixed relations, then you might be forced back into just privileging some units. Right? So if we don't go down this route, then we're left with distance ratios and mass ratios. And how difficult is it to go from there? Well, if we look at the history of relationalism, which is what I'm going to do now, we're going to see first that the task is very difficult, especially if we adhere to these conditions that I placed on reduction according to the narrow view. But part of looking at the history of relationalism will also be to see that we can actually make a lot of progress once we sort of abandon these three principles. And so we'll look at that, and then that'll naturally lead us to a reduction of neutron gravitation theory with respect to the scale symmetry. So, relationalism, what is it? So Leibniz sort of lays it out in the following terms. I have said more than once that I hold space to be something merely relative, as time is, that I hold it to be the order of coexistences, as time is an order of successions, what space denotes in terms of possibility an order of things which exist at the same time. So, we have, so the structure that we're allowing ourselves here is sort of much barer than the structure that we have in gravitation theory. We have instantaneous particle configurations, and these are sort of given some temporal succession, some order of temporal succession. So this is sort of what relationalists would like to see. That's what we're going to work with. And well, for a long time, it didn't look like we could make much progress. If we look at the history of trying to get this to work, trying to come up with a physics that allows us to do this. So one thing here to note here is that there were several attempts at writing down Lagrangians explicitly in terms of interparticle distances and relative velocities, but these just didn't lead to empirically successful theories. They were sort of empirically inadequate. They couldn't replicate the success of Newtonian gravitation theory. A second point to mention here is that Lagrange managed to write down equations for the n-body problem explicitly in terms of interparticle distances. But then you get into all sorts of trouble because these will in general contain third derivatives and new constants for angular momentum and total energy. So this is all discussed in Ollie's survey article. So I think, and then the history of relationalism progresses, and one important observation that I think people made was that the equations simplify drastically if the angular momentum is zero, and then the derivatives and the new constants vanish, right? And what people realize is that we can find relationalist theories if we do not attempt to capture sort of possibilities that Newton countenances, where the global angular momentum is non-zero. Obviously, what's going to happen if we do this is we're going to end up with a theory that's not empirically equivalent to Newtonian gravitation theory. But that might actually be a feature, not a bug, as is commonly recognized. So I think that to summarize sort of the lesson from this is that if we look around the universe and we find that the overall angular momentum is not zero, then we shouldn't want to be relationalist in the first place. But if it is zero, which it appears to be, I gather, well, we should want our theory to actually predict this. Right? That would be nice to have. And so I think this insight sort of led to the sort of milestone success in the relationalist program, which is Barber-Bertotti theory. And so what I want to say is that Barber-Bertotti theory is a clear example of a successful reduction, but it doesn't fit the bill that we've outlined. We talked about the narrow view. It violates both the explicit invariance condition and the empirical equivalence condition. And I would say all the more reason not to have those, all the more reason not to insist on those. Let me walk you briefly through how Barber-Bertotti theory is constructed so that we can get a sense of why it fails, why these conditions are not met by the theory. So, it's supposed to be a relationalist theory. So what is physical, according to the theory, is a, temporal succession of particle configurations, as we saw in the Leibniz quote. So what we have to work with here is sort of relative distances between particles within one configuration, or within any configuration. But what we don't allow ourselves for the theory is absolute distances between particles, because those would allow for sort of trans-temporal length comparisons, which relationalists are sort of not happy to countenance. We don't have a temporal metric, and we don't have sort of orientation relative to absolute space, nothing like that. So how do we get to Barber-Bertotti theory? Well, we start out with the configuration space of a Newtonian gravitation model, and then we quotient this by translations, rotations, dilatations, and this gives us this reduced space that we call shape space. And then this is sort of the arena for the models of Barber-Bertotti theory, right? The shape space, and then a model of Barber-Bertotti theory is a curve image on that shape space that meets certain conditions. So the way we get to the models of Barber-Bertotti theory then is that we define a metric on the shape space, and then the dynamically possible models. The models of Barber-Bertotti theory are the geodesics with respect to that metric. But this is done in a sort of, and this is sort of crucial to the argument, this is done in a sort of very indirect way. It sort of it makes use of the full configuration space fairly liberally, right? So the way it's done is that we have a kinetic metric on the full configuration space, on the Newtonian configuration space. And this metric sort of appears in the Jacobi action here, which the stationary points of which give us the Newtonian models that are allowed. And there's then a way to get from that to a metric on shape space via this procedure that Barber and Bertotti call best matching. And the way it works is that we essentially, so if you have two paths through configuration space, which sort of meet the condition that they traverse exactly the same equivalence classes according to what the relationalist thinks the equivalence classes should be, right? So the classes that we have in our quotiented shape space, well, then we get different lengths assigned to these paths in general, but we can extremize these paths that we have by variation under the structure that the relationalist thinks of as redundant. So we can vary the action with respect to rotation, dilatation, and then under the right conditions, this yields a well-defined metric on shape space, and that was what we were looking for, and then that gives us our models of Barber-Bertotti theory. But as I say, it has to be sort of the right conditions, right? So what are these? Well, this only works if the total angular momentum is zero, and there's also, it needs to preserve something called the dilatational momentum. So this is x times p. So this needs to be preserved, and moreover, what's sort of the most dramatic of all is that this only works if the potential that we're using is actually not of the 1 over r form of the Newtonian potential, but we need to have potentials that satisfy that are sort of the 1 over r squared kind. Now you think, well, that's pretty. Yeah.
Here you're considering also quotienting scale, right?
Yeah. So if you don't get this, if you don't do that, if you just best match with respect to rotations, and you don't get this last condition, and the second one neither. So these really arise from actually quotienting by scale as well. Yeah, that's crucial. But okay, so but you can do this, and you get a neat theory out at the end. I want to say that strikes me as a clear success case of reduction, but nonetheless it violates these two conditions: the explicit invariance condition and the empirical equivalence condition. So to see that it violates the explicit invariance condition, at no point do we get dynamical equations in terms of relative distance or anything like that. We don't write that down ever. So that's one reason to think that so shape space is defined via quotienting. And finally, the geodesics on the shape space are obtained by extremization of the action on the full configuration space. So we're sort of at various points in sort of getting to Barber-Bertotti theory, we are just helping ourselves to the full configuration space in these various ways. So Julian Barber talks about this last point a little bit. He says that if you try to do it directly on shape space, it's just super messy. You can't do it. That's why he proceeds in the way he does. It seems to me fairly clear that the theory does not meet this criterion of being explicitly formulated in terms of the invariance. And then empirical equivalence, well, that fails too. We have these conditions: the total angular momentum must be zero, the dilatational momentum must be zero, and the potentials are just not of the right kind. So we don't recover any of the models of NGT, strictly speaking, right? In the sense that's sort of laid out in the model recovery criterion. At the same time, however, Barber-Bertotti theory has the resources to re-establish empirical adequacy. So as Barber explains, there are sort of two ways you can go there. The first is to note that under certain conditions, so if the distribution of particles, if the system meets certain conditions, if it's virialized and a globular cluster, then an appropriate choice of 1 over r squared potential can replicate the Newtonian predictions very accurately. And the second point he makes is that one can always choose a scale invariant potential that sort of yields the Newtonian forces plus some compensating weak universal force, where that's sort of negligible in most cases. So there is a way to get sort of quasi-Newtonian predictions out. There are actually two ways. So the theory is not obviously empirically inadequate. Okay. And now what I want to claim is that helps us with reducing Newtonian gravitation theory with respect to the scale symmetry. So that was our original goal. And I mean, we're almost there, so to speak. So Barber-Bertotti theory is already almost a reduction of Newtonian gravitation theory with respect to that symmetry. What remains to be fixed is this dependence on the mass scale. So we still have absolute masses in Barber-Bertotti theory. The solution to that is just to combine ideas of Machian comparativism, the theory that Niels Martens constructed that we saw earlier, and Barber-Bertotti theory. The basic idea would be just to apply best matching to a Machian comparativist configuration space instead of the Newtonian gravitation theory configuration space. need to, make some tweaks, but that would be sort of the basic idea, and that works just fine as far as I can tell. And if you do that, you get the final theory that we were looking for, which I call, SBBT, so scale invariant theory, if you like. Yeah.
Sorry, just to make a slight correction, because I didn't remember, but now I checked. The Barber-Bertotti doesn't quotient out scale. It was introduced much later, 2002, by Julian.
So, I mean, there's sort of the early version, and this is sort of a later version. It's all labels, I suppose.
But the recovery is done for Barber-Bertotti theory that works without the scale part.
Yeah, that's true. So you can. So if you don't quotient, so if you stick to the sort of the early version of Barber-Bertotti theory where you don't quotient by scale, then you can just exactly recover the zero angular momentum models of Newtonian gravitation theory. So that works. The trouble then is if you do it for scale as well, which obviously I need to do because I'm interested in that scale symmetry, then you can't do it exactly anymore for any model because you have to insist on these 1 over r squared potentials. But it's correct that sort of the original version that Barber-Bertotti introduced still had an absolute length scale, and then you can recover the zero angular momentum models. Where was I? Right. Okay. So if you combine Machian comparativism and BBT, then I think you can just get to a theory that eliminates the scale symmetry, and I would call that a reduction of Newtonian gravitation theory with respect to the scale symmetry. Now, obviously, I want to defend reduction. I want to say that reduction is sort of a viable way to go still, and we have not seen any good reasons for sort of dismissing it in favor and preferring sophistication across the board. So I need to sort of also make the case that the theory that I've come up with has sort of some advantages over the theory Caspar came up with, this sophisticated version of Newtonian gravitation theory. The way I see it, it has sort of 3 advantages. The first is that it has great predictive strength, so it actually predicts that the angular momentum of the universe is 0. It seems to me more structurally parsimonious because Caspar had to sort of elevate the status of the gravitational constant to a function to get it to work, right? So he had to sort of introduce this cross-value space structure to get his theory to work. In SBBT, we don't need that. We don't need to introduce this cross-value space structure. And then it has this feature which I call harmony, which is that every kinetical symmetry, so every value space automorphism is a dynamical symmetry, which in Caspar's theory is not the case because mass value space, as he has it, for instance, is invariant under scalings, but a pure mass scaling is not a symmetry of the theory. And then I think a more general advantage of reduction is that, I'm just going to touch on this very briefly now, but I think there has been a lot of sort of complacency in the sophistication camp about this idea of anti-excitism. I think it's not obviously a viable metaphysical doctrine. There are good arguments against it, and in any case, you might not want your theories to be sort of hostage to the standing of this doctrine, right? So it might be nice to just not have to worry about whether anti-excitism is true, to sort of avoid this sort of standard underdetermination issues that one gets, right? And so I think one general reason to try and get reduction to work is that you don't want to be an anti-excitatist, or don't want to rely at least on anti-excitation. And I think, reduction can give you that. Okay, so that's sort of the end. You'll all have your own questions, I'm sure, but I've sort of written up a few questions that I sort of found most pressing. No need to, think about any of these or address any of these, but I just thought I'd put them out there. So the first question would be, given that SGBT does not, strictly speaking, recover any of the models of neutron gravitation theory, does it deserve to be called a reduction of neutron gravitation theory? I've argued yes, but I mean, maybe there's some good grounds for pushing back on that. Relatedly, are there good motivations after all for the empirical equivalence condition? Maybe I've overlooked something. Maybe it can be motivated after all. Are there good reasons, sort of analogously, to accept the explicit invariance condition? Is there something sort of wrong with theories that don't have it? Are theories that don't satisfy that condition somehow, cheating or falling short or inadequate in some other way? Then the fourth question is of broad picture. I mean, what should we take the aims of reduction to be? This is something I touched on earlier when I said one way to think about it might be, this sort of wheat from the chaff picture. Just get rid of the surplus structure, keep everything that sort of plays a role in the theory. But then I thought there might be a sort of a wider, broader way of thinking about the aims of reduction, which is just to try and get rid of all structure that strikes us as problematic, all structure that we are sort of we find dubious. So that's one thing I try to motivate, but maybe there's some room for pushing back on that. And then the final point is what I just called this harmony idea that every kinematical symmetry is a dynamical symmetry that is, I take it, strictly stronger than Ehrman's second symmetry principle. Then the question is that nice? Is that really a desideratum, or is that too much to ask? Is there anything wrong with theories that don't have it? I find it an attractive feature, but Adam has suggested to me that it might be just too much to ask. There's not really, there's nothing wrong with theories that don't exhibit this. So, might be interesting to think about that. All right. Well, thanks very much.
Okay. All right. Okay. So, questions, starting with Enrique.